Okay, good morning, everyone. Good afternoon, good evening, depending on when you're watching this. Today we will have an asynchronous lecture. I don't really like teaching asynchronously, so even if not everyone has their video on, I do enjoy seeing people's names and their photos and their participation orally, their participation on the chat, the questions that they ask, the answers that they offer. So I do miss that today, and I appreciate your accommodation. Today I have a funeral, and watching this asynchronously, of course, so later on in the day I will be available on Slack, and we can communicate with any follow-up questions. So today we are going to continue our discussion, our presentation, our lectures on graph algorithms. We began that topic last Thursday, and we're going to begin with two examples of real-world examples of graphs. The second picture is an abstraction of the subway system, right? So being able to go from stop to stop is an example of a graph, right? The stops are nodes or vertices, and the tracks, if you will, between them represent edges. The first example is from Jeff Bezos, the CEO of Amazon, and he has a rule called the two pizza rule. And the idea is that he tries to keep his meetings small enough so that he can feed them with two pizzas. Now, Jeff Bezos can afford many, many pizzas. He doesn't need to be cheap. Why is he doing this? And the answer is because he recognizes that the complexity of a meeting is essentially n squared, right? Every person there has a certain dynamic with every other person. And so that's like an n squared. So he says, let's keep that n down. So if you figure two pizzas has 16 slices, each person eats 2 slices on average, that's 8 people. That keeps it down to 8 times 7 divided by 2, which is 28 interactions rather than that number as it grows when n increases. All right, so let's review a few concepts from last time. The basic graph is vertices and edges. Vertices are also called nodes. Edges are also called arcs. And the edges represent a relation between the vertices and themselves, a relation over the set of vertices. We talked about unweighted graphs where either an edge exists or it doesn't, a 1 or a 0 in terms of the representation, or it can be weighted. In a weighted graph, each edge has a cost associated with it or a value, but it's a number, and the number doesn't necessarily have to be a 1 or 0. We also discussed what do you do in the case of a non-existent edge. Do you indicate that with an infinity as the cost, or do you indicate that with a 0? Both approaches are out there. If you're looking at source code on Geeks for Geeks or any other site, you need to pay attention to which approach are they taking because it changes the code. All right, we can have directed and undirected graphs. Directed graphs are the graphs where the edges have arrows on them indicating whether it's from A to B or from B to A. If it goes from A to B and B to A, it will actually appear as two edges, one with an arrow one way, one with an arrow the other way, as opposed to an undirected graph. An undirected graph is automatically symmetric. It's assumed that if I can go from A to B, I can go from B to A and vice versa. We discussed the concept of a degree. A degree is the number of nodes, the number of neighbors that each vertex in the graph has. And if it's a directed graph, so the number of neighbors coming in, the number of adjacencies in, and the number of adjacencies out are not the same. And so we differentiate between what we call an in degree, which is vertices coming in, edges coming in, and an out degree, how many edges are leaving, going outward. We had 4 representations of graphs: the adjacency matrix, which is a V by V matrix, which has a 1 to indicate that the edge between I and J exists, a 0 otherwise. We have the adjacency table, which is a list of all the vertices, and for each vertex, it's a linked list, generally a linked list of the neighbors. Okay, the edge set, which focuses on the edges that exist. Okay, so a little less focused on the vertices. It says these are the ordered pairs of edges, or it's ordered pairs of vertices that form the edges. And then we had the hash map, which uses as a key a possible edge, and then it would have a 1 to indicate, or a true to indicate that the edge exists. Keep in mind that the data structure that you choose for the graph to represent the graph will impact its time. Generally speaking, the bigger the data structure, the more the time, but it doesn't always work like that. For example, in an adjacency matrix, which is a bigger data structure, you will get better performance on determining whether an edge exists than in an adjacency table, even though adjacency table is smaller. All right, we have some special graphs, okay? So these are good to know. The most basic special graph is a tree. In a tree, the number of vertices is always one more than the number of edges, right? A tree needs to be connected. It needs to, it cannot have any cycles. Okay, cycle's not a loop. A cycle is going from A to B to C and back to A, right? That's a cycle. If we add an edge to a graph, we create a cycle. And if we remove any edge from a tree graph, then we disconnect that tree. We disconnect that graph. A cycle denoted by CN means the entire graph is one big circle. I go from A to B to C to D to E to F and back to A. That's called a cycle graph. And we have the complete graph. Okay, notice that complete graph is denoted with the letter K, K for complete. Well, we already use C for cycle, so we can't use C for complete. So we use K to indicate that it's complete, which means that every vertex in the graph is adjacent to every other vertex. And we know how many vertices and edges we're going to have. Bipartite graph, we had that at the end of last class. Bipartite means we can divide the vertices into two sets, right? All the edges exist between two sets. No edges are within a set. And last class, we had an algorithm using colors, right? We colored adjacent vertices, opposite colors. And if we ever came into a situation where we couldn't color the vertex what we wanted to because it was already colored by the other color, then we know it's not bipartite. We can't divide it up neatly into two sets. A regular graph has a very specific non-regular meaning, and regular means that every vertex has the same number of edges. The degree of all of them are the same. And finally, we have a star graph. A star graph is a tree, and it generally looks something like an asterisk, meaning you have a dot in the middle, and then you have pointers, you have edges to all the other vertices. And because it's a tree, the number of vertices will be the number of edges plus 1. The degree of each vertex is 1, except for the one in the center, which has a degree of n minus 1. So it's absolutely not a regular graph, right? So here you see it. Here is a tree. Here is a cycle. Here is a complete graph of orders, looks like order 7. This is a bipartite graph, looks like a complete bipartite graph, 3 by 2. This graph, I don't know if you can tell what it is, but that is a regular graph, right? Each vertex has 4 neighbors, all right? And finally, we have the star graph over here. One question that I've asked in the past on exams is to, for a given graph, determine if it is a cycle graph, determine if it is bipartite, determine if it is a complete graph. So you have to write some pseudocode that is able to do that. All right, various traversals. So we had the breadth search, which is a level order traversal, which means we visit a node, then its children, or its neighbors, then its neighbors' neighbors, then those neighbors' neighbors' neighbors, and so on and so forth, as opposed to a depth first search, where we visit a vertex, and then we see where we can go from there. We try to go as far as we can, and when we can go no further, we back up one, see if we can go somewhere else, go try that as far as we can, and when that fails, we back up, and we keep on doing that. Eventually, we'll back up to where we started, and we try again. All right, we also talked about taking a DFS and enhancing it, recording the start and stop times, or the, we call it the discovery and finish times, D and F, for each vertex. And we showed how we can use those discovery and finish times to classify each of the edges in the graph as one of these 4. Tree edge is an edge which is used to discover a vertex. A back edge is from a descendant back to an ancestor. A forward edge is from an ancestor to a descendant, but not a tree edge. And finally, we have cross edges, which are sort of like between cousins. It's saying it's not an ancestor-descendant relationship, and it's not a descendant-ancestor relationship. It's something else. Okay, so this is the example. You can go back to the slides from last time. We have a lot of applications of DFS. So we just mentioned classifying edges, but we can also use it to detect cycles. Basically, you see if you hit a vertex that you already hit before. All right, bipartite testing, we discussed that last time, right? Are all the vertices divisible into two groups such that all the edges are between them? And we use that coloring argument. Spanning tree to find the minimum number of edges that is required to create connectivity in the graph. Shortest path, right? That's for unweighted graphs. We'll talk about that for weighted graphs probably today. Transitive closure, we actually gave 3 algorithms for the transitive closure. One algorithm was using DFS from each vertex. We talked about using Warshall's algorithm, which is a dynamic programming solution, O of V cubed. And our third algorithm was using matrix multiplication with Boolean addition, right? So a somewhat unlikely approach, but one that works. And topological sorting, where basically we take the vertices in DFS order and output them in reverse finish time. All right, so we just talked about the transitive closure. We have the all pairs shortest path, Floyd's algorithm, and we will hopefully review that again today. All right, so what we're going to start with here after that review is solving the all pairs shortest path problem. What does that even mean? It means for each vertex, I would like to know how to go to every other vertex. So that's why it's called APSP, all pairs shortest path, because for every vertex to every other vertex, I want to know what is the best way to do that. By the way, that's not what Waze does for us or our other GPS, right? Waze takes a specific source, a specific destination, and it finds us the shortest path between that source and that destination. It looks at many different paths along the way, but it's single source, single destination. Okay, this is all pairs to all destinations, right? So how do we do that? Well, one possibility would say, let's try every single possible path between the pair. We call that an exhaustive search. And not surprisingly, that is going to take exponential time, not really practical, what we call an intractable approach. Another approach is to take an algorithm that solves the single source shortest path problem, SSSP. All right, we have not really studied that yet, but the approach that is usually used for that is something called Dijkstra's algorithm. There is another algorithm called Bellman-Ford. All right, Dijkstra is probably the more common one, but Bellman-Ford is also used. One of the advantages of the Bellman-Ford algorithm is that it permits negative weight edges. So Dijkstra's algorithm breaks down. It does not work if the edges can have negative weights. We'll talk more about that later on, but Bellman-Ford will work if they're negative weight edges, not for negative weight cycles, but negative weight edges. The third approach, which is the one we're going to start with, is an algorithm that is designed for this problem, for all pairs shortest path. And the algorithm we have for that, it's not the only algorithm, but it's the one that we teach. It's called Floyd's algorithm. Floyd's algorithm is very closely connected to the Warshall algorithm we already saw for transitive closure. So what is Floyd's algorithm? Well, the first thing is it uses dynamic programming. Okay, dynamic programming means we start with the simple cases and we gradually make them more complex. So more specifically, we start with paths of length 0. That means I'm going from a vertex to itself, right? There are no other vertices there. So that's a path of length 0. Then we go to paths of length 1, right? Going directly from a vertex to another edge. We think of paths of length 2, which has one intermediate vertex, specifically vertex 1. Can we do anything going through vertex 1 to our other, our destination vertex? Then we try it with vertices 1 and 2, using the information we already have about vertex 1. So we gradually build up until we're allowed to have n-1 intermediate vertices. We never have more than n-1 intermediate vertices, because why should we? That means we're going back to a vertex more than once, and just cut the slack, right? So if I'm going from A to B to C to D, back to A, and then to F, just go to A to F the first time around. You'll save some time, right? We have this Floyd's algorithm is very similar to Warshall's algorithm for the transitive closure problem. The difference is transitive closure just looks at connectivity. It says, can I get from vertex I to vertex J? It doesn't care about shortest path. It just says, can I get there or not? Yes or no, true or false. That's why we can use Boolean addition for that. So how do we actually implement Floyd's algorithm? Well, we have two helper arrays or storage arrays. So in that sense, the space complexity is going to be order of n cubed, or n is v, right? V squared, I should say, right? It's a two-dimensional vertex, two-dimensional matrix or two-dimensional array. Why? Because for each vertex, we need to know how to go to every other one. So the distance tells us the shortest path, shortest distance. The predecessor array tells us how do we get from I to J. So it says, what is the immediate predecessor of J in the path from I to J? So here's the code, right? We had this code already in dynamic programming. Here we have it again, and there are two loops, or two sets of loops. The first set of loop is for initialization. The second set of loops is for the actual real processing. So what does the first loop do? It does really two things, maybe three, depending on how you count. So it sets up the distances, initializes them. And it says initially, the cost of going from I to J is just the cost of the edge from I to J. Okay, there is no other path that is available to us at this point. And the predecessor of going from I to J is just going to be I, because again, we're going directly from I to J. So what is the predecessor? The predecessor is going to be I, right? What is the distance from a vertex to itself? So remember this, okay? The cost of going from a vertex to itself is generally considered to be infinity because there is no edge. But the distance, which is not the same as the cost, is the cost of the path, the entire path. And the path doesn't exist, right? It has length 0. So the cost is just 0. And the predecessor of I going to I doesn't exist because there is no predecessor. So we use -1 to indicate that, right? Now we have the loop itself, the main loop, and we use K as our intermediate vertex. So I is the source, J is the destination, K represents, it's a loop variable, but it represents intermediate vertices. And the basic idea of the code, and you know what, this parentheses is extraneous, so we're going to take it out, right? So the basic idea is it says, right? Take a look at that line I just removed the parentheses from. It's saying as follows: if I can go from I to intermediate vertex K, and from K to intermediate, from intermediate vertex K to J, right? Less than whatever I could do already from I to J, which may include some intermediate vertices, but not intermediate vertex K. It's saying then we need to update. So the new distance, the cost from I to J will be the distance from I to K plus the distance from K to J. And the new predecessor from I to J is going to be the predecessor from K to J. Okay, a common mistake when people see this is they think, oh, the predecessor is going to be K, but that's not true because there may be several vertices along the way as we go from K to J. So it's saying, what is the predecessor of J as we go from K to J, which is the edge just before, the vertex just before J on that path. Okay, and here we have an illustration. This is not something we want to track by hand because there is a lot that's getting updated, right? Think about what's getting updated. In every single iteration, we are potentially updating n by n. So if you have 10 vertices, by 10 vertices, you're updating 100 things, and you're doing that for each intermediate vertex. So here is a worked out example from Wikipedia. Let's just analyze that algorithm. So we had two loops, right? This loop is a nested loop, so that is n squared. This loop is 3 loops inside each other, so that's going to be v cubed. And if we look at the total time is v cubed. Okay, the space complexity of this is v squared. Okay, so now we get to shortest path problems more generally, and we can break them down into 3 different categories. We have the all pair shortest path problem, which we just discussed. That was Floyd. We have the single source shortest path problem, which is going to be Dijkstra. And we have the single source, single destination, which, as I said before, that's what you're usually solving with your GPS, whether you're using Waze or MapQuest or anything else. We're going from one point to another. We want to figure out the best way to do that. And again, our focus is on weighted graphs, right? Where not all edges are created equally. So we start with Dijkstra's algorithm. Dijkstra's algorithm has been around for 66 years. I like to point out an interesting linguistic phenomenon about Dijkstra. You have the letters I, J, and K in a row, which doesn't happen that often in English. All right. It uses a greedy strategy. Okay, so we can add this to our list of greedy algorithms. Back when we discussed greedy algorithms, I said we studied some in class, and then I said there are more to come, right? Dijkstra's algorithm, Prim's algorithm, Pruskel's algorithm, Huffman coding, as well as many approximation algorithms. So here we are for Dijkstra's algorithm. The story goes that he was on a date with his fiancée in a cafe, and they needed to get to another city in Europe. And he used an algorithm, which he made up on the spot, wrote it on a napkin in the cafe, and it later became published as Dijkstra's algorithm. So it uses a greedy strategy, which means it looks at what is locally optimal. It says, if I can go from here to a few places, let me choose the closest one. And the reason that that works is because the weights are all positive. So if I'm taking something that is less expensive, that will be better overall than if I take something more expensive. If I can have negative weight edges, it is possible that later on, I may take a long route now, but it'll be offset by something negative later. If there are no negative weights, it's only going to get more expensive to get somewhere than less expensive the more edges I include, right? So this is the key line here, all right? So we'll see it in the code itself. Let's understand that when we start. It's saying as follows. The cost of going from the source. And notice we don't, for the distance, we don't have ij. We don't have uv. We have u. Why? Because the source is known. So we don't have to provide the source to the array. It's a one-dimensional array instead of a two-dimensional array because we're always starting from the same point. It's called the single source shortest path problem, not the all pairs shortest path. So that's why this array looks like that. All right. So this is, so this is the key line. It says, if I'm going from the source to u, and then I take an edge from u to v, if that is less than whatever I could do to go to v before, then we want to update. We want to update because we're saying I can go from the source to v better than whatever I could do before, right? So this is the basic idea of the proof, right? The proof says as follows. We're using d here instead of dis, just for short. And the idea is that this is going to, we take the shortest way to get to a particular vertex because it's only going to increase. So that's what I explained before. If you have negative weight edges, that's not true anymore because I can maybe spend a little bit more to get somewhere, but later on, I'm going to have negative weight edges, and that's going to reduce it. So here is some pseudocode for Dijkstra's algorithm. Like Floyd's algorithm, it has 2 parts. It has an initialization part, and it has sort of the main part. And let's go through each part. So for our initialization, we have each vertex by itself, right? And we say, okay, the distance of going from the source to any given vertex is infinity, right? Because right now I don't have a path yet. That's going to change soon. But right now I don't have a path yet. And what is my predecessor? If my predecessor is 0. In Floyd's algorithm, use -1. It really doesn't matter. The point is I don't have a predecessor yet. right? And then I say as follows. For the vertex itself, the source, the distance is 0, right? There's no cost of going, no distance of going from the source to the source itself. So we make that a special case and we say that's 0. Now here's what we do. We go through the vertices one by one, and we take the vertex, the other vertex that is closest to this one, right? We take the vertex in the set S with minimum distance. This line here is the greedy strategy. I repeat, this line here is a greedy strategy. It says, look at all the distances, take the one that is smallest. That's the greedy strategy. So we take it out of the set S and we look at its neighbors. And we say, and this is what I warned you about before, this is the key line here. So it's not the greedy strategy line, but this is a key line. It says that if I can go from the source to U, and then from U with one more edge to V, and that's less than whatever I could do to go to V so far, that means that's a better approach. I'm better off going through U, and I'm going to do that. So I update my distance to V, and the predecessor V becomes U. Notice that this is different than what we had in Floyd. In Floyd, if I looked at the predecessor of, let's say, I to J, it was the predecessor of K to J if K is an intermediate vertex. And then we return both of these. Both of these data structures are important to us. So here is an example. This is a directed acyclic graph. I'm sorry, I take back the acyclic part. This is a loop-free graph. It is directed. You can see arrows on the edges. And I have a very worked out example for you, right? So remember how this works. We start with our set S and we gradually remove things from it. So a few things to help us understand this example. Number one is that in each line, one or, well, not necessarily something, but there may be something that is underlined. Underlined means it's getting updated in that row, and we'll go through some of the rows to help you understand that. The other thing, there's a color coding here, right? So something is turning red in each line, and that's the one that's chosen. Okay, so let's go through this. So initially, and X, by the way, is my symbol for infinity here, all right? So what this is saying is as follows, right? In most cases, the distance is going to be 0. Well, I take that back. The distance from the source vertex to itself is 0, and the rest are infinity, and the predecessor is 0. So we take one of them, right? Which one do we take? Well, initially we take this one, and we update. We say, can I go from vertex 1 to this other vertex? So we say, yeah. If I go from 1 to 2, let me move my face out of the way. So I can go from 1 to 2 with a cost of 2. So my new distance is 2, and my predecessor will be 1. Let's look at the other one that got updated, right? It's saying I can go from 1 to 4 with a cost of 1, and now my predecessor is going to be 1. Okay, then I look through this and I say, which one should I choose? It's the smallest distance. So I have 2, infinity, 1, infinity, infinity, infinity. I take the smallest one as 1. This one becomes red. And I update. I say, well, by going through vertex 4, can I do any better? And this one changes. It says, yeah, I can go from 1 to 4 to 3 for a total cost of 3. 1 plus 2. So that's why this became 3. This one also became 3. I can go from 1 to 4 to 5. I don't know if you can see that. I'm in the way again. So 1 to 4 to 5. Cost of 1 plus 2 makes 3. That's why this became 3, and the predecessor is 4. This one also changed. I can go from 1 to 4 to 6 with the cost of 1 plus 8 is 9. And I can go from 1 to 4 to 7 with the total cost of 1 plus 4 makes 5. All right, I do the next line. How do I pick that this one's red? I look at all the distances that are remaining. 2, 3, I ignore the red ones. 3, 9, 5. The smallest is obviously 2. This one gets chosen. Nothing got updated here. And the next one, I take the one that's smallest. The next one that's smallest is 3. And this one got updated. Why did it get updated? Because now I can go from 1 to 6 right? So I can go from 1 to 4 to, sorry, I'm going through 6. What happened here? Give me 1 second. I'm going from 1. I could do it in 9. Oh, yes. Take a look at this. Everyone see this? I'm going from 1 to 4 and 4 to 2 and 3 to 6. So the total cost there is 8. So that's why this became 8, because by using vertex 3, I now have a shorter way. Before I could go from 1 to 4 to 8. That was a cost of 9. And now I can go from 1 to 4 to 2 through intermediate vertex 3 to 6 for a total cost of 8. So that's what happened there. All right, so work through this example, put some time into organizing it so that you could see every little step along the way. All right, here are some Python code for Dijkstra. For those not familiar with Python, self just means it's sort of cumbersome. Basic means a reference to the item, let's say an attribute of the item itself. So sort of ignore that. Assume that wherever you see self just means there's a local variable that's available, class variable that's available called v, right? Notice that self is being passed in. All right, so what are we doing in this code? All right, so let's walk through it together. We are initializing our distance array, okay? Originally, we're saying that it's an array of length v, right? So times means that dimension, right, of size v, and everything is infinity when we start. The distance to the source itself is 0. The predecessor array is initialized to 0, v zeros, and we mark everything to as visited as false to indicate that we haven't been there yet. All right, so we iterate and we say as follows: find us the minimum distance. Now, what I don't show here is how to find the minimum distance. We'll talk about that in a little bit, okay? But that particular function, that method, is not shown. We mark it as visited, so now we've seen it, and we look at its neighbors. That's what this is saying, right? Look at all the neighbors of that particular graph. And we say, okay, so look at this line here. Why are we checking that it's greater than 0? Because this particular code, which came from Geeks for Geeks, this particular code is assuming that the cost of edges that don't exist is 0 and not infinity. So that's what I warned you about. You have to check, right? Does the edge even exist? If the edge doesn't exist, then don't use it. So that's what this is here for. This is not really part of Dijkstra's algorithm. This line is just saying if the edge exists. If the edge exists and we have not visited that vertex yet, then we decide, are we going to use it? We use it if the cost goes down. If I go from the source to u and from the u to v, there is that extra edge, and it creates a total cost that's less than whatever distance we had already. Update it, right? Say that's going to be the new distance. Go however you go to u, one more edge to v, and that's the new distance, and the predecessor is going to be u. All right, so there are a few pieces to this that we need to talk about. How do we actually do it, right? One of them is this line here. How do you find the minimum distance, right? So there are some options here. One option is you have an array, and you look through the array and you find it. That would take order of n, order of v. There are v possible neighbors. Another thing we need to do is update the neighbors, find the neighbors and update them. So that's what's going on here, right? Look at all the neighbors and update them. So that's another piece of this. How do we do these? And the answer is, it depends. The answer is there are different choices. We want to pick a choice that works, and not only works, but works well. So we have a few different options here, okay? Option number 1 is to use an adjacency matrix for the graph, and we store these distances in an array. How do you find the minimum? Well, the array is not sorted, right? It's ordered by the vertex number, not by size. So how do you find the minimum? You have to go through the whole array, That's going to take order of V time, right? How do we find neighbors? Well, we go through the row of the adjacency matrix. We look for the ones, or we look for the costs that are not zero, not infinity, depending on how it's implemented. So that also takes order V. And we have to do that, right, over all vertices. So that's going to take V squared, right? Because we got to find the min for each vertex, and we have to do the updates. We have to find the neighbors. So that's V squared. V squared is not bad, but we also know it's not great. Just like we don't like bubble sort and selection sort and insertion sort, certainly not when we have big arrays. We don't really like V squared if there is a better option. The question is there a better option? And the answer is yes, but it's going to take work. So the first thing we do is we change the representation of the graph. Instead of an adjacency matrix, we switch it to an adjacency table, or what most people call an adjacency list. Why is that preferred? Because to find the neighbors doesn't take order V. It depends on the actual number of neighbors. So if you have fewer neighbors, it will take less time to find the neighbors, right? The second change is how we store these distances. So instead of storing them in an array where it takes order of V time to find the min, we store them in a heap, all right? How long does it take to find the min in a min heap? Well, it's actually order 1, constant time. That's great. The problem is there's a little bit more work than that. We have to restore the heap. We have to do a heapify. How long does it take to heapify? It takes log of V, right? Because that's the height of the heap. So let's think about how much work we are doing. We have to, for each vertex, we have to find the min, and we have to restore the heap. So that's going to be V log V, just like N log N, V log V. But we also have to update neighbors. And how many neighbors do we have? Well, for any given vertex, we don't know. We could have as many as V. But the total number of neighbors is E. The total number of neighbors is E, because how many edges are there total? There are E of them. So the total work, okay, take a look at this last line here, second to last line. We have V log V for finding mins and E log V for updates. So the total time is the bigger of those. It's going to be E log V. Okay, option number 3. Option number 3, again, assumes we're using an adjacency table or list for the graph. So that has not changed. But what is changing here is how we store these distances. And instead of storing them in a regular binary heap, we use a Fibonacci heap. What is a Fibonacci heap? So we had a picture of a Fibonacci heap in our lecture on advanced tree and heap structures. It's not really a heap per se, okay? If we assume that a heap needs to be a tree, it's a forest, okay? It's a set of trees. And what is the advantage of it? The advantage of it is that because the trees are broken out, each one will be more compact than they are otherwise. So once we identify which heap we want, we will be able to find them more quickly. We'll be able to update more quickly. So just to be more specific, okay, it will still take us order 1 to find the minimum. It will still take us log V to heapify, but the updates to the Fibonacci heap are constant time, or what we call amortized time, which means not how much any given operation is going to take, but if we look at all the work overall, comes out to, it's almost like a kind of average of order 1. So if we put that all together, once again, we have V log V for finding mins, but we, instead of E log V for the updates, it's E times 1, or just E. So the total work is E V log V. So again, we have 3 approaches: adjacency matrix with just an array of distances. That takes V squared. We have an adjacency table using a traditional min heap. That takes E log V plus V log V, or E log V. And then we have, using a Fibonacci heap, another alternative is something called a binomial heap. And in those cases, it's E plus V log V. Now, which of these is going to be bigger? Well, that depends on the size of the graph. Generally, if the graph is dense, meaning it has a lot of edges, then E will be bigger than V log V. If it's a sparse graph, not too many edges, then E could actually be less than the V log V. All right, here by the way is a Fibonacci heap, right? So you see it doesn't have a full tree structure, right? Because you got stuff in different places. And it has multiple roots, all right? The beauty is that each of the roots is relatively shallow in terms of the tree that it, or the subtree that it points to, and that enables the updates to happen quickly. Now, what I want to show you in this picture here is the effect of a negative weight edge. So remember how Dijkstra's algorithm works. Dijkstra's algorithm says, if I have two choices, how to get to something, I take the shorter one, right? So I say, okay, I need to go from A somewhere. I'm going to go to 2 because 2 is less than 5. So anything more that would take me to B would increase the cost. But that's not true anymore if there are negative weight edges. So look at this. If I go to C this way, right, it costs 2. If I go to C this way, it costs -5. Everyone see that? 5 plus -10 is -5. So Dijkstra's algorithm, that greedy strategy, no longer works. Okay, if I have negative weight edges, no longer works. So we need another approach. So Dijkstra's algorithm is great, but it assumes that there are no negative weight edges. Now, we're going to introduce another algorithm called Bellman-Ford momentarily. But I want you to understand before we even get there that Bellman-Ford, while it works for negative weight edges, it does not work for negative weight cycle for a very interesting reason. So take a look at this. If we have a negative weight cycle, what does that mean? It means the entire cycle has a negative cost, right? So 5 plus -10 plus 4 makes -1. Then nothing is going to make sense anymore. Why? Because it's saying I can just go around and around in a circle as many times as I want, and I will keep bringing the cost down. Keep bringing the cost down. Now, here's a question for you, which is, do we even have negative weight edges in real life? Or is that just, something hypothetical for a computer science algorithm? And the answer is, it doesn't happen that often, but it can happen. For example, I don't know if this is still true, but I knew that once upon a time, they actually would pay people to take the bus to go to Atlantic City, right? You would get a free bus. I think they even gave you some food, and they would give you not money, but they would give you coins, chips that you could use to play games in Atlantic City. So you could take a bus from New York or New Jersey or Delaware, different places, and you got paid essentially to do that. And there are people who would actually take that and they would get together with their relatives in Atlantic City, and they wouldn't gamble at all. They would just take advantage of the free ride, the free lunch, and the free chips, which they would then sell to someone else. Okay, why do they do that? The way they do that, the reason they do that is they assume most people will not be able to resist the temptation. They will go to the casinos, they will spend a lot of money, and it won't be a negative weight edge. It won't be a positive weight cycle, right? So that's what they're hoping for. But, it's possible, right? If you have a negative weight cycle, that you could just keep doing that over and over and over again and just accumulate, all that negative weight edge. Okay, so that brings us to the Bellman-Ford algorithm. Take a look at these dates, all right? 1955 is before 1956. 1956 is when the dynamic, the Dijkstra's algorithm came about. So already there are hints to Bellman-Ford before Bellman-Ford, right? Ford was 1956, Bellman was 1958. Someone already came up with this algorithm before that. Somehow Bellman and Ford got credit for it. There's also another guy here who did it, but okay. So ignoring who deserves the credit for it, that's Bellman-Ford. It also uses dynamic programming, not like Dijkstra. Dijkstra uses greedy algorithm, but it uses dynamic programming like Floyd's algorithm. All right, so again, dynamic program should trigger in your mind. It means we have an incremental approach. We gradually build up. And let's take a look at the code here. So like Dijkstra's algorithm, like Floyd's algorithm, we have an initialization part and we have a main part. We do have one other part, which I'll discuss in a moment. So initially, this is going to look like Dijkstra's algorithm, right? The distance to each vertex is infinity. The predecessor of each vertex is 0, right? Because I can't get there at this point. And then we say that the distance to the source is 0 because I'm going from where I am now to where I am now. So there is no cost to that path. Now here's where the dynamic programming comes in. It says for all the vertices, for each edge in the graph, I check. So if I can go, this should look like Dijkstra's algorithm. This line here should look like Dijkstra. The whole thing isn't like Dijkstra, but this line is. It says, if I can go from the source to U and one more edge to V in less than whatever it costs to go to V already, then that becomes the new best way to get to V. So I go to U, I take that additional edge from U to V, and my predecessor of V is going to be U, right? So I do need to do one more thing here. And remember, I warned you that we cannot, even Bellman-Ford does not allow negative weight cycles, so we have to build in a check for that. So at the end, we check that if I can further reduce the cost by doing it again, I can get the cost down even further, the same pair of edges. That means that there's a negative weight cycle, and I'm returning an error condition. So it's not just a message, but it's basically saying that the computation that we just did is not meaningful because there's a negative weight cycle, and I can just keep reducing the cost to negative infinity. So the whole thing just doesn't make any sense anymore. All right, so that's the algorithm. What's the time complexity? Well, let's go walk through it, right? We have a loop here. Loop is O of V. We have a nested loop here. The outer loop is order of vertices. The inner loop is order of the number of edges. So this loop here is V times E. And then we go through the edges one more time. So that's going to be E. So we have V plus VE plus E. And obviously VE is the most expensive part, right? So let's just, okay, so we don't have an analysis page here. Oh, here's our analysis. Okay, so I just snuck that in over here. The total time is O of V. And maybe I'm just going to amend that. So we'll say time is O of V for the outer loop. Then we have O of VE for the inner loop. And then, I'm sorry, for the second loop. And then O of E for the third loop. And the total time is OVE. So just make that a little bit more clear. And now we move on to a third algorithm, okay? The third problem, I should say, which is the single source, single target, or sometimes we call it single source, single destination. How do we do that? Okay, so remember, Bellman-Ford found us the cost from a vertex to all other vertices. Dijkstra's algorithm solved from a source vertex to all other vertices. Floyd's algorithm solved from every vertex to every other vertex. So how do we do it if I only have a single source and a single target? Something like Waze or MapQuest or any of those algorithms. What do we do? So I have some choices here. And again, when we study analysis of algorithms, we don't just want to think what is the right answer. We want to consider several answers and to be able to compare them. So one approach, I'm not saying it's the best approach, but one approach is to take Floyd's algorithm, right? So keep in mind that you might not come up with this A star search that we're going to discuss in a moment, right? But you should be able to solve the problem some other ways. You could say, well, I could use Floyd's all pair shortest path problem. I'll plug in the S and the T, and I'll pull out the cost, the distance that I want. So it's not a great approach, but it's an approach. And when you don't have a better approach, take the worser approach, right? So it's going to be V cubed, which we know from the beginning of today's lecture. We could do Dijkstra's algorithm for S and then plug in, find the distance from S to T. I should be more careful. All right, I should really write it like this. So the distance array in Dijkstra's algorithm would just be this. Okay, so it's really right. We don't have two parameters there, so I should really write it that way. Okay, and we have Dijkstra's algorithm. We can also stop once I get to the t, and depending on the implementation, right, we have 3 different time complexities. Okay, and we have a third approach. Okay, so this is approach you wouldn't know unless you've learned it before. It's called A-star search. A-star search. I don't know why it's called A-star. I'm not really sure. And it basically has 2 components here. Okay, 2 costs that we put together to figure out, to estimate the cost of going from the source to the target. All right. And what are the 2 parts? So the G of n is the actual cost. Okay, it's the actual cost of going from the source to an intermediate node n, meaning we know what that cost is. But we don't know the cost of going from that intermediate node n to the destination. Okay, so what is the rest of it? And for that, we use an estimation. For those of you who are also in 355, we will see something like this coming up soon when we do networking. Because think about in networking, right? I want to go from one router to another router. What is the best way to go? That's an example of a single source, single target. I want to go from the source IP to the destination IP. Or if I've already arrived at a particular router, what's the best way to get from that router, which is now my source, to the target? And the answer is we may know up to a certain point what the optimal is. So that's the G of n. And we may not know from there how to go. So we take an estimate. Let me explain why in networking you might have that. Because you start in what's called an autonomous system, which means those are a bunch of routers that are all part of some kind of group. And they share information with each other very freely. So you have perfect information. And with the perfect information, we can get an exact number. We run, let's say, a Dijkstra's algorithm on that. The problem is that that number only reflects a small inner circle of vertices, or in the case of networks of routers. It doesn't give us the big picture. I need to get it to Africa. I need to get it to Asia. I need to get it to Europe. I need to get it to Australia. So I have the local routers, let's say in the New York area, but I don't have all that other information. So for the other information, I only have an estimate, right? So that's what this H of n represents. It represents an estimate. So again, we have 2 parts, right? The G of n is the exact cost, and then we have the heuristic, all right? So in terms of the best cost, the optimal cost, we can use any of the algorithms that we've discussed already. But again, it usually reflects a very small set of vertices. Then we have the other part, all right? And how do we find it? So we can't get an exact number because that's going to be too expensive. So how do we do that? And the answer is we have a few different measures of distance. Okay, so I'm just showing you what we have going on here, right? Let's just move this out of the way on the bottom. Move this out of the way at the top. I don't know if you can see that, but it's bothering my screen. All right, so red is our source, green is our target, and we need to go along the way. So again, the motivation for this A-star search was robotics, right? Think about, I don't know if anyone has one of them. I don't have one of them, but it's all, those little robots that clean your, vacuum your floors. So what do? They move around, and when they bump into a wall, or they bump into a couch, or they bump into a file cabinet or a chair or something, so they move around, right? So that's what's happening here. We're trying to figure out how to go from here to here without bumping into the gray things, or we bump into them, we have to move around them, can't go through them. So how do we estimate distance? And for this, we have a few heuristics. So let's just see here. Okay, 3 distances. For those of you who are math majors, you may have taken a course in analysis, and you may have discussed this, these different distances in an analysis course. So one is called the, we're actually going to start with the last one. Okay, the last one is called the Euclidean distance. So this is the distance you learned back in high school when you talk about Euclidean geometry, or maybe, you know, in 11th grade math when you're, you know, dealing with functions and things like that, right? So basically you're taking the, you know, the difference in the x coordinates, and we've discussed this Euclidean distance in a number of occasions in our course as well. You take the difference in the x coordinates and you square it. You take the difference in the y coordinates and you square that. You take the square root of the whole thing, and now you have a distance. So back when we talked about closest pairs, when we did, I don't know if it came up in convex holes, maybe it came up in convex holes also. So a number of occasions, right? That's what we call the Euclidean distance. In terms of our picture, it says ignore the black boxes, ignore the grids. What is the distance between here and here? Well, you say, okay, what's the difference in x? So it's 1, 2, I'm sorry, the difference in x is 1, 2, 3, 4, 5, 6, 7 is the difference in x. So take 7 squared, all right? And the difference in y is 1, 2, 3, so it's 3 squared, all right? So 7 squared is 49, 3 squared is 9, 49 and 9 is 58, square root of 58 is 7 point something, right? That's one distance. Our next distance is the Chebyshev distance. Okay, so Chebyshev says, I can't, you know, it's not the way like the bird flies, right? But I'm allowed to cut through diagonals. Okay, so again, I'm still not paying attention to the gray boxes, but I'm allowed to go at any given move. I can go northeast, south, or west, but I can also go northeast, northwest, southwest, southeast without an additional cost. In other words, going northeast is the same as going north or east. So north and east would count as 2, northeast would count as 1. In the Manhattan distance, it's the way you're supposed to walk in Manhattan, which means you do 1 block northeast, south, or west, and you can do another block in another direction. You're not really supposed to cut through diagonals. And of course, in Manhattan, it's hard to cut through diagonals because there are buildings everywhere. So there are some occasions where there's a park and you can, you know, cut through the park on a diagonal. But for the most part, we have buildings everywhere. So you're really forced to go down the streets, either, you know, southwest, south or north, or east or west. So we call that the Manhattan distance. So the Manhattan distance in this case is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Because I can't go diagonals, and I certainly can't go one big diagonal, so the cost is 10. So these are all heuristics, okay? Why are they not exact numbers? Because in reality, none of those are really correct. I have to worry about the gray boxes, right? I actually once gave this as a problem to a student. So I gave them a maze, sort of a fun assignment. It's a little difficult to code the A* search, but I gave them basically you know, blocks, you know, blockades in different positions, and the algorithm had to work its way around it. All right. If the heuristic score is 0, so that becomes like Dijkstra's algorithm. That's not A*. So again, the assumption here is there is a portion of the distance that is not known, that I have to use an estimate in order to find it. So here is some code for it, and that is going to be it. Okay, so we're going to stop our asynchronous lecture here. I will be available later on today on Slack. For those in 355, we will be having class at 8 o'clock, but you probably will not have watched this video then, but it is in the announcements. And next time we will continue our discussion of graph algorithms. So coming up, we have the minimum spanning tree problem, two versions for that. We have Prim's algorithm, and we have Prim, and we have Kruskal. We will also talk about something called the max flow problem, and probably a few other things will show up there as well. So that's it for today. Everyone have a good day. I will see you tomorrow. And again, if you have any questions, you can message me on Slack and I'll reply later.